Okay, so we're going to dive back in a little more to the idea of molar mass conversions, which has a lot of synonyms in it. So, and I use them interchangeably, and so will a lot of people in your future experience in school. So I just want to make sure you understand the function of these numbers, and you can call it whatever you want to, but I use molar mass a lot. You might also hear molecular weight. Atomic weight is related, right? So you basically take all the atomic weights of a molecule and add them together to get a molecular weight. But if you just have an element or an ion by itself, then you could call it atomic weight. I think that a molecular mass is another one too. So I think that about covers it. There's probably more, but basically all of these have the same units. It's grams per mole, and there's some kind of number there. So that's like what we were doing in the last video, and it's all dimensional analysis. So even if you have no idea what to do, you can start by just writing out the number and the unit. And you're going to find it very helpful if you also write a chemical with the number and unit, because in a little while we're going to be converting between moles of one chemical and moles of another one. And it's way easier to keep track if you're in the habit of having a name with your unit and number. So then we have to know how to name stuff, right? So you should always give these a shot before I do them. So pause the video and try it. But ammonium is NH4 plus, and chloride means Cl minus, and so these will come together with one of each of them, like that. And so to go from grams into moles, we need to use the molecular weight. Again, that comes from adding everything up in the periodic table. So like nitrogen says 1401. Hydrogen says 101 per hydrogen. And chlorine says 35.45. So we just add them all up. Don't forget to multiply by 4 for the hydrogen. Like that, okay? So if I wanted to measure out 1 mole of NH4Cl, I would have to get, oh, I didn't even write the total here. The total is 53.5 grams per mole. So if I wanted to weigh out exactly 1 mole, I would put in 53.5 grams. I don't have 1 mole, I have 4.5 grams. So I can actually flip that over to cancel the grams this time. So it's kind of the reverse of the last example, where we used molar mass. But that works because we were saying 1 mole of ammonia equals this many particles. We'll call this a molecule because it's covalent. And it also equals 53.5 grams. So all of these are true statements, and I can create ratios out of whatever I need to in order to convert, right? And so here, what I'm going to put in the calculator, of course, is 4.5 divided by 53.5. And we get 0.084112149. My unit will be moles, and my chemical will be NH4Cl. Oh, I guess I didn't talk about this explicitly. Sometimes I write out the whole word mole. Sometimes I abbreviate MOL. Do not abbreviate just M, because just M means meters. Okay, so MOL or MOLE. All right, and so anyway, this is not the final answer though, because I need to think about the significant digits. So our measurement has 2 significant figures. The numbers from the periodic table should not be what limits you. If it does, you need to take more numbers. And actually in this case, I got it wrong because I had 2 decimal places on all my numbers. So this is actually 3.50, like that. But anyway, so the number from the periodic table should not be what limits your figures. So here our measurement limits us, which is good, which means I only get to keep 2 sig figs. The pause was so you would think about what our answer is, right? So the leading zeros are not significant, so we're going to round to this place value. All right, and so that's our answer for the first question. I want you to pause it again. Try to answer the second question on your own. So NaCl, we get to the mass of, we kind of looked at it earlier, but NaCl has a mass of 35.45 for the chlorine and 22.99 for the sodium. So you get to 58.44 grams per mole. So there's our molecular weight. And so if we know 0.652 moles of the NaCl, we know it's going to be dimensional analysis. And I've already said if we're kind of going between mass and moles or moles and mass, then you need to use the molecular weight. So that's why I calculated that right off. But my unit is grams on top and moles on the bottom, so I can use it just like I wrote it to begin with, because I'm trying to cancel moles. So these are the two different ways. Either you're going to use it with grams on top, if you're trying to find grams, or you're going to use it with moles on top, if you're trying to find moles. You'll notice that I'm not using the number that we have in my conversion factor. So one thing that can happen, like here, is people might say 58.44 grams per 0.652 moles, but that's wrong. Okay, it's always, if you're getting it from the periodic table, it's always worth 1 mole, and so you're trying to use that fact, that conversion factor, to cancel moles and get it into what we're asked after, which is of course grams here. So in my calculator, I go 0.652 times 58.44. I don't ever bother dividing by 1 because I know that doesn't change it. But it helps you do that just to keep track of your units. And so the calculator says 38.10288. I have 3 significant figures, so I'm going to say 38.1 grams of salt. So that's our answer there. All right, so I said we were going to be converting between the amount of one chemical in moles to the other chemical in moles, and we have to go through that process because our chemical reactions give us ratios between molecules. They don't give us ratios between masses. And we already said different substances have different masses for the same number of particles. So we have to have a connection that goes through moles using a chemical reaction in order to tell how much of anything is produced or how much of your other reactant gets consumed. Anytime we're converting between one chemical and another, we have to go through moles. So here's how it works. So for example, a simple formation reaction, which means from the elements. Oh, this should also say gas here. And this happens very quickly, very easily with just a little bit of energy input. If you have hydrogen and oxygen together, they'll explode, and the product of that is water. And you'll notice these numbers in the front. These are called coefficients. So I'm gonna just make squares out of them. So coefficients are just like the coefficients from math, right? So if I say 2x, the coefficient is 2. If I say 2y plus 3, the coefficient is still 2, right? So whatever comes after the coefficient applies to everything after it. In math, it would be like 2y and 2 times 3, like that. Here, when we say 2, we mean 2 of this whole particle that's after it, right? So 2 hydrogen molecules react with 1 oxygen molecule, and they're going to produce 2 water molecules, right? So if we think about it as molecules, so we have 2 molecules of hydrogen, and we have 1 molecule of oxygen, and we're going to make 2 molecules of water. Easy enough, right? But we can't count molecules, all right? We can't separate just 2 hydrogen molecules and 1 oxygen. So the connection is between using Avogadro's number is using what a mole is, okay? So we can also think about this reaction in terms of moles. You can say there's 2 moles of hydrogen that will react with 1 mole of oxygen, and you're going to produce 2 moles of water. And now, if we're thinking about this in terms of Avogadro's number, we know that 2 moles would be twice Avogadro's number, right? So it'd be twice that many molecules. And you could figure that out if you want to, right? And of course, it'll react with exactly 6.022 times 10 to the 23rd molecules of oxygen. Okay? So these ratios, these whole number ratios, are the relationship. This is called a 2-to-1 reaction because 2 parts of hydrogen react with 1 part of oxygen, and you get H2O, which has 2 parts hydrogen to 1 part of oxygen. Okay? So the number in front of a chemical reaction gives us a molecule, rather. The number in front of a molecule in a chemical reaction gives us a lot of information. You can have a picture in your head of 2 molecules of hydrogen. Remember, hydrogen's the diatomic, so is oxygen. And so you have 2 atoms there. So this is one H, and here's another H. And the same thing over here because the coefficient has 2 in there. So we have 4 total atoms, right? So you can even get to total atoms just by going the coefficient times the subscript. Okay? So we have 4 hydrogen atoms, and we better have 4 hydrogen atoms on this side as well. And we do, because this red 2 applies to the hydrogen as well as to the oxygen. That's the conservation of mass that Lavoisier was talking about in the beginning. All right? And so you can also, in addition to picturing it as individual molecules, you can also picture it as moles, because molecules and moles are proportional to each other, related to each other by Avogadro's number. Now, to go from moles to mass, we have to think about those conversions, right? So 1 molecule of hydrogen weighs 1.01 grams per mole times 2. So you can do that math inside of there if you want to. And that's where they get the value of 4 down here. It's 2 times 2 essentially. Same thing here. It's 16.00 grams per mole times 2 because of the subscript. And that's where you get 32 grams from. Okay. Now you'll notice the reactants, that's everything on the left, everything I'm reacting together. The weight of the reactants are going to add up and equal the rate of the products. That's conservation of mass. And that's true for all reactions. All chemical change has to have mass conserved, meaning we have the same number of each atom at the end, and we have the same total mass in the beginning that we have at the end.